Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about a very interesting and very popular topic, Dyson sphere. So let's dive right into it. Well, what the heck is this Dyson sphere? It's one thing that you have to understand before we dive any deeper into it. It's not a sphere or a shell. That's just done by basically one Star Trek CG artist. It cannot be simply because engineering, material science that is required to make a sphere that can encompass a whole star without collapsing into it. It's on such a different level that if you have that, you will not need to build a Dyson swarm. So flat out, it's not a sphere, it's not a shell. You do not cover the whole star. That just simply cannot be done. However, it is a swarm of multiple small units. So you might be like, why the heck we say if it's multiple small units, why the heck we say it covers the whole star? Think of it this way. It's equivalent of creating a forest around your star. So if there is a forest between you and something that you want to see, you can't see that thing. Is a forest blocking 100% of it? No, but like one tree is not blocking it. If you have enough of them, then there is no direct path. That what will happen. So once you have multiple multiple small units covering the whole star in different orbit, different inclination, and all that, from let's say 5 light years away or 10 light years away, you will see there is supposed to be something. There is a star's gravitational well is there, gravitational effect is there, gravitational lensing is there, but the star cannot be seen. It will glow directly in infrared simply because energy cannot be created nor destroyed. But you will not see the optical spectrum, you will not see the X-ray, you will not see the gamma rays. You will just like, okay, it's just infrared. So that's why the idea has this kind of sphere mentality. Basically, the effect is like you just cover the whole planet. Basically, if you zoom in, you're like, okay, I can see the star. But you zoom out, like light year by light year, you're like, after some point, you will not see anything once the swarm has reached full capacity. Now, this idea was coined, quote unquote, in 1960s by Freeman Dyson, this guy. And the idea was basically he was working in some science project, and the idea was, how the heck will you know that there is an advanced alien civilization? Basically, figure out mathematically what an alien civilization would do, that you'll be like, okay, that's it, that's an alien civilization. So he came up with the idea that even if you have nuclear fusion, which we do not have right now, but even if you have nuclear fusion, there is a much better, much more abundant, much more powerful energy source if you directly convert your star as an energy source. No matter how small the star is, you can have a red dwarf, you still would exceed the power output of anything you can do from a planet. So this idea, mathematically, they did the mathematical model, can it be done, physics, science, and all that. And the reality was that if you want to do it, it can be done. Physics is not stopping you, and I'm talking about physics that is under known science. That is something we can do. That is something that we use to build our satellites and create Starlink, something like that. So the mathematical idea is there. That's the whole point. If you want to extract 100% of energy of your star, this is how you will do it. You'll not make one magical sphere made out of magic material. You'll have multiple power satellites, collectors, or you may even have a whole habitats that are swarming around. And if you have enough of them, that from outside you will reach a point where it's like, dude, I can't see the star, because it's like almost like a forest covering the whole planet. I'm saying whole star. You will have reached Dyson sphere territory. So why the heck we want to go this bonkers? Like, this is like ultra level bonkers. So why the heck we want to do this? One thing you have to understand inherently is that humans are so superior to every single other animal is simply because of energy. We all started on the same playing field. Basically, we all had eat food, convert that into chemical energy. Your chemical energy would be used by your muscles, and you get the work done. In that regard, surprisingly, majority of our animals are better than us. However, we started to extract extra energy using fire, using chemical energy, and that way we reached on a whole different level. That's the whole point. So the next level would be directly proportional to the energy. So like if you have two countries, one country have YOLO amounts of energy, they don't even have to think about it, they're going to be progressing much faster, much further than a country that has to give a damn how the heck it's getting electricity and how is it reliable, sustainable, and all that jazz. So you have to know, energy is our fundamental building block. Another aspect of it is that the more progressive we become, the more successful in terms of our lifespan. Basically, we started as poor as in like health wise as 30 years. Basically, you will only live 30 years, and if you are lucky, like generally something else will end you. Now, it was not that like nobody else could live to 90 in 1800s or 1500s. It was just that majority of the people were ticked off by either plague, diseases, dysentery, diarrhea, chickenpox, things of that nature. So as we start to live longer, flat out our energy consumption will go higher and higher and higher. Because again, let's assume you have kids in 30s and you are living till you are 150 years old. Now the amount of people, if you do that, then the whole population will grow exponentially. So you will have a scenario where you have to consume a lot of energy. So our population is kind of limited in terms of our Earth's population is directly limited to energy production. So we have to have unlimited energy. Now sun has more than enough. That's the one good thing about sun. It's like YOLO, bro. If you extract even 1.0000000 few zeros, add as many as you want, 1% of it, the complete energy of this, yeah, you're sorted for the whole life. Because you have to understand, the sun is a three-dimensional object. It's a sphere. It radiates energy in all direction uniformly. Now again, there are some dark spots and all that, but zoom out enough, it's like, yeah, it's a uniform thing. So can we capture that? No, flat out. Why? Because we do not have signature. We do not have enough surface area. Like Jupiter and Saturn and Neptune and Pluto, Pluto, Jupiter, Saturn, Uranus, and Neptune, they are barely visible against them. Barely. Like, this is a huge boy, this is a tiny boy. And Earth is so tiny that if there is a coronal mass ejection, the magnetic, U shape that it will create will fit inside it. So you have to understand that we do not even have enough surface area to extract even 1% out of sun. So it's like even sun is giving like take all need to use, and we need energy. We just don't have enough surface area on sun. So how the heck you will solve this problem? You flat out cover the sun itself. Basically, like, where's the best place to put the solar panel? Directly on the sun. So it's that kind of logic. It's like you want energy, sun has more than enough. And like when I say more than enough, I mean truly in billion year sense it has more than enough. But like again, we'll reach a point where even if we cover 100% of sun surface, basically Earth's surface in solar panels, which you do not want to do given the fact that you want to live inside it, it's not doable. So that is why the swarm idea is so applicable to scientific civilizations. It's like this is the ultimate end game. What about the physics? Because we are, as a human creatures, we can get carried away with emotions and all that jazz. So can we do it? Well, yes, 100% under known science, this is thoroughly allowed. It does not require anti-gravity, it does not require warp drive, it does not require EM drive and all that jazz. It's like what we know today, what we utilize today, we can do this if we want to. Now, you have to understand, energy cannot be created, not destroyed. So if you are covering the whole planet, basically whole star, what the hell will happen? Basically, all the energy that is coming in every spectrum, basically X-ray, gamma rays, the whole high energy spectrum, it will be converted down into the waste heat. So the sphere that we have constructed around the forest of tiny habitats or power satellites, they will radiate all that energy away, waste heat in infrared. So from outside perspective, you will look at there's supposed to be a star, it's not there, but it has an infrared signature that will will match the energy output of a supposed star, mathematically speaking. And that's what the sphere mathematics was done for. It was like, okay, make a telescope that detects specifically infrared spectrum and try to scan all the stars. If you find a star that matches this kind of mathematical model where it's like they're supposed to be star, we can't see the star, but the infrared signature output matches what star is supposed to be there is a good chance there is a Dyson swarm there. So that's the whole point. And the solar turbine that we need for something like this, because we do not have to build solar cells. Like we tried this, it works. Again, we have been using this for 40 years. We know this works, but it's not scalable. Like if you cannot do this for hundreds and thousands of square kilometers, let alone a whole surface of the sun. That simply cannot be done. However, mirrors, we can do that. Mirrors, because again, you can make them as thin as few atoms thin in case of aluminum, and tada, you are reflecting more than enough energy to run a basically concentrated solar system, and you will get more than enough energy conversion efficiency that you don't have to think about it. That's the whole point. Once you exceed basically exceed as in terms of height, exceed the Earth's atmosphere, you don't have to think about conversion efficiency. It's like more than enough is there, more than enough. So in terms of physics, everything that we need, we have tested it in small scale, one way or the another, and science is there. Science is solid on this. Now, what about engineering? Because again, science is also very far out. We can do anything. We can even build solar railway, but engineering is like, bro, this is stupid. So is engineering on this side, like as in practical wise? Short answer, yes, because while we cannot build a sphere, we can put things in orbit. Because we have controls over rockets, thrusters, and all that jazz, we can have the orbits in different inclination. And we have been doing this on Earth. Like you can see that, like this is the Earth model, and this band is geostationary band. So we have practice with this. Like this is something we have covered our celestial body in satellites. And once Starlink goes online with like its full satellite, it will like complete coverage. So it's not something that unheard of. It's just larger scale. Basically, take this, turbocharge it. Basically, this is a 1G phone. Imagine 5G or something like that. So that's one route. You just orbit with power collectors. Second option is satellites you make. Now, yeah, that's a weird name. I can't really say that properly. But the idea with that is like once you go close enough to a star surface, there is a very unique point where you will not fall onto it. Why? Because let's say this is sun surface. You're falling, but here's the gravity is strong, that's absolutely true, but it's the luminance, basically the light energy that is coming off of it, it's also strong, it's very strong, it's sun, for crying out loud. It will start to push you. Now if you are lightweight enough that you can reach a point where your surface area and everything balances out, you will literally not fall. Why? Because light is pushing you up, gravity is pulling it out, so there you will literally reach a point where you can get static. Basically this will be a static satellite. You just put it there, again you will have some thrusters to compensate or spin it to stabilize it, and that's it, done. You're gonna stay there. Like it will look very odd, very weird. It's like stuck, directly stuck. There is no motion. Like it will move with the star, but it will not have any orbital motion with it. So that can be done. Physics is there, engineering is there, but we never built it anything like that. So we do not know. But more and more people are like into the orbit side, because again we know we have built it. It's a known thing. Now okay, you were like, okay, let's say we built the mirrors, we concentrated the energy, we made YOLO amounts of energy. How the heck you gonna deliver it from point A to point B? Simple answer, microwave. Now why microwave? A, we know how to use it. B, you are using this where there is a very good chance you have a mobile phone. There is a very good chance it's having a microwave receiver. So what is that? Power transmission from point A to point B. Right now, the mobile tower is not giving you power simply because that's not his job. His job is to give signal. It's like, yeah, I'm going to give you a signal. What's the first thing you do? You receive the power. Basically, you receive actual electrical energy. You boost it up using an amplifier. You're getting there. Same thing when we are talking about basically direct to home satellite TV. Your satellite is giving actual electrical power. It's just designed in such a way that is like, hey, let's cover the whole country rather than like, give the 1 watt of power to this one guy. We covered that. That's why we need huge amplifiers, huge antenna and all that. But physics is there. In terms of microwave, we can go even further, where we, instead of like having a dish that is just blasting it out, we can have phase shift array technology. Basically every beam can be focused in such a way that you're basically making a laser, and you can be like, okay, tada, take power from point A to point B. And in vacuum to vacuum transfer, that's absolutely amazing. Even in terms of atmosphere, and if you're directly going through the atmosphere from top to bottom, you're going to get very high efficiency. In terms of converting it, that's also very high efficiency. So that's the engineering aspect of it. It can be done with orbital technology that we have right now. And in terms of satellites, I'm not that sold on that. However, microwave delivery technology, again, we are using it already. So what about small satellites, small scale test of it? Because again, you do not build a big house and just like tada, you build it brick by brick. So is there any small scale equivalent for this? Short answer, yes. And right now more and more people are looking into this, simply because a lot of people are getting fed up by nuclear fusion, which includes me. Is simply because like, yeah, we burnt a billion for few years, and for few decades we have been burning billions and billions, and every time the answer is like, yeah, next reactor that will we build, which will cost like 10 billion and 20 billion, might achieve it. I'm like, at some point people are like, dude, the amount of money we burnt at this point in time, it's so much that we could have built entire solar farms, which would have made enough energy that energy could have been used to make another solar farm production systems and unit, as in like from mining to manufacturing to transporting and all that. And we could have literally created a runaway effect where it's like, yeah, solar energy to make more solar energy. We could have reached that years ago. So many people are like kind of fed up with this idea. And is there any true alternate, as in like all green technologies have side effects, all of them. This, as in like space-based energy, has no side effect within the context of our reality. So people want to go directly in space. Why? Because if you are in geostationary orbit, you have one advantage. You have to make your antenna face down. That's it, done. You don't have to move your antenna. What about on ground? Again, same thing. That's why your dish TV is in the fixed location. It does not have to move. It does not have to track. It does not need space. It's like point-to-point contact. Awesome. Now, because of the orbit distance is so huge that you are rarely in the shadow of the sun. Basically, normal satellites, they barely go to around 1 hour of shadow time. So your night, quote unquote night, is barely 1 hour long. Or you can tilt the orbit a little bit in such a way that you can maintain it and all that. You will still have the same geostationary orbit point, but you will never go into the shadow of Earth. Benefit: 24/7 power, continuously 365 a day. Like there is nothing to block your energy up. And your pipeline, microwave can directly go through clouds and all that. That's why your mobile phone works. So we can do that, and Japan has already started to like build a basic foundation in 2015. So many people are already working on it, and that was the one I found out. So we can start today. Everything about this we can start today. And when I'm saying start today, I do not mean like, okay, we're gonna have hundreds of megawatt of power, tada, take it and go. No, first we'll be barely like, okay, let's try to transfer 1 kilowatt of electricity. Then we'll slowly start to figure out how to make the microwave link. That's the weak part right now, microwave link. How the heck we make that link more efficient? How do we have conversion efficiencies and all that? That's right now the weak link. But again, we can do it within known science, and we can start today. Let's say somebody shows them, builds a demo model that works in, let's say, in low Earth orbit rather than geostationary, and we figure it out. Okay, that's how we're gonna do it. Then somebody launches another refined version. We can do this right now with Falcon 9 technology, with Falcon Heavy technology. We do not even need some magical hoop. It can be done right now. And it will solve all our problems simply because it's giving us energy without the side effect of that. And it does not even have waste energy problem in terms of nuclear fusion, which has that waste energy problem. It's like, because your conversion efficiency won't be higher than like 30-40%, best case scenario. So that 50% energy is wasted here. Now microwave transmission, again, the unit that is in space, that's not that efficient, but the energy that you are getting is in microwave format. Converting microwave into electricity is very efficient. You are talking about 80 plus efficiency. And if we start to do in large scale, we can achieve 90%. At that point, the wasted energy would be very little. So it's awesome in that regard also. And we can just keep scaling it up no matter how big we want. Like, we can keep scaling it up. So that's what the future holds. Like, people have started to look into this much more seriously. It's like, the more people realize like hydro dams, it's a no-go. Solar farms, simply what you're gonna do in night time. And power storage, yeah, that's not. Battery, you cannot build enough gigafactory. We do not have enough minerals cheap enough that you can be like, yeah, we're gonna strip mine the whole planet just to build batteries. Yeah, that's not a go. And in this, even if you do not want to tilt the orbit, you're like, hey, tilted orbit is not that stable. No problem. You just have two of them, like 1 hour apart in terms of orbit, right? So one will always give you power. So it can be done right now, today. We can start today. Now, why are so people excited about this? Well, in terms of hope, it represents on a different level. The hope, scale, scope, power, it's on a different level. We cannot basically count for it, because it will make us scale too. This Cordovez scale that we have, it's not that refined of a scale. People don't actually want to use it. It's just popular in science fiction. That's why people talk about it. But the idea is basically at scale 1, basically 0.1, you are capturing 100% of the energy that is falling onto your planet, whichever the planet is. If you're a big planet, you have to capture more energy. If you're a small planet, capture little energy, and that will put you level 1. We are not here yet. Level 2 would be, you will capture the whole energy output of your star. That is what we are talking about today. And the level 3 is basically capturing the whole output of the whole galaxy. So you can see this scale is not really that practical. It's just like, it goes from okay to maybe to what the hell. So it's not that awesome. But in terms of our capability, we can start today. We can start like very little, solar satellites. We are barely collecting. Let's say we start practically 100 watts. Then it will be like kilowatt. Then it will be megawatt. Once we reach megawatt, we have to go to solar concentrated, because solar panels at that energy rating would become ludicrously expensive. And again, we don't have enough minerals, but we have more than enough aluminum in moon also. So we don't even have to strip mine Earth itself. So we can do a lot of things. And once we start to basically lay the foundation of it, it's like, okay, first satellites that are collecting power from space, once they start to go, everything will have a runaway effect. Basically, first one, energy go, then you sell enough electricity to justify the cost, and then you use that energy to build a second one. Once you do like 5-6 of that, doubling effect will start take over. Once you have doubling effect, tada, humanity no longer gives a damn about energy. It's like, yeah, we don't give a damn. We don't think about it. It's like, energy, how much you want? 50, 60 trillion gigawatts, we got this. It's like, we ain't got time for that. Like, electricity board will disappear at that point. So that is why we are so hopeful about this. And it is doable. It does not require EM drive. It does not require pure drives, warp drives and all that. It's done, known, absolute physics, real. And again, we are using small scale right now. So this was my presentation on this whole majestical concept. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. If you liked it, enjoyed it. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your disappointment, and please leave a comment, because I try to reply to all of them. Subscribe, press the bell icon for free, and as always, thanks for watching.